Theorem of Total Probability. Now, as you progress in your studies, you'll notice that we often encounter situations where an event, let's call it event A, doesn't just happen in one single way. Instead, it can occur through several different, mutually exclusive scenarios. This means there are different, separate paths that could lead to the same outcome. Because of this, if we want to find the overall total probability of event occurring, we can't just look at one single path or one single scenario. If we ignore any of the possible ways event could happen, our final calculation will be incomplete. We must carefully account for every possible way or every possible scenario that could lead to event A. This brings us to the core of our lesson, the Theorem of Total Probability. This theorem is the essential tool we use to bring all those different paths together to find that one single, overall probability. In the next slide, I'll show you a great way to visualize this using the concept of paths to a destination. Welcome, everyone. Today, we are going to dive into a very important concept in probability theory known as the Theorem of Total Probability. Understanding the concept. Now that we've introduced the idea that an event can occur through various scenarios, let's dive deeper into the intuition behind this concept. To make this easier to visualize, I want you to imagine that event A is a specific destination you are trying to reach. To get to this destination, there isn't just one road. Instead, there are several different, distinct paths you could take. In mathematical terms, we represent each of these individual paths as an event, which we can call E sub 1, E sub 2, all the way up to E sub n. Now, it is crucial to understand that these paths form what we call a partition of the sample space. When we say they form a partition, we are making two very important claims. First, these paths are exhaustive, which simply means you must take exactly one of these paths to reach your destination. There are no other hidden routes. Second, these paths are mutually exclusive, meaning you cannot be on two different paths at the same time. You pick one and only one. So, how does this help us? The Theorem of Total Probability gives us a powerful way to calculate the overall probability of reaching destination A. We do this by calculating the probability of reaching A through each individual path, and then summing all those probabilities together. This sets the stage for the mathematical derivation we are about to see in the next slide. Mathematical derivation. Now that we have a conceptual grasp of using different paths to reach a destination, let's move on to slide 3, where we will mathematically derive the formula. To truly understand why this formula works, we aren't just going to memorize it. Instead, we are going to break down the logic into small, manageable steps. First, let's look at step 1, expressing event A in terms of the partition. Remember from the previous slide that our paths, E sub 1, E sub 2, and so on, partition the entire sample space. Because these paths cover everything, any event A that happens must happen within one of these paths. Therefore, we can write event A as the union of its intersections with each partition element. In mathematical terms, A equals the union of an intersection E sub 1, union a intersection E sub 2, and so on, all the way to a intersection E sub n. Essentially, we are saying that event A is just the collection of all the different ways A can overlap with our various paths. Included in the text above. Moving to step 2, we apply the addition rule. Now recall from our definition of a partition that these paths are mutually exclusive, meaning you can't be on two paths at once. Because the paths don't overlap, the intersections we just mentioned, A intersection E sub 1, A intersection E sub 2, and so on, are also mutually exclusive. This is a crucial point. Because they are mutually exclusive, the probability of their union is simply the sum of their individual probabilities. So, the probability of A equals the probability of an intersection E sub 1, plus the probability of an intersection E, and so on, up to the probability of an intersection E sub n. Next, in step 3, we apply the multiplication rule. We can refine this further using the definition of conditional probability. We know that the probability of both A and E sub j occurring is equal to the probability of E sub j multiplied by the conditional probability of a given E sub j if we substitute this logic into our previous equation, our formula transforms. Now, the probability of A equals the probability of E sub 1 times the probability of a given E sub 1, plus the probability of E sub 2 times the probability of a given E sub 2, continuing through to the probability of E sub n times the probability of a given E sub n. This brings us to our final formula. To make things cleaner for higher-level mathematics, we use summation notation. The theorem of total probability is expressed as the probability of A equals the summation, from j equals 1 to n, of the probability of E sub j multiplied by the probability of a given E sub j. This formula is the engine that will allow us to solve the real-world quality control problem we are about to see in the next slide. Real-world example, quality control. Now that we have understood the mathematical derivation, let's apply it to a real-world scenario to see how it works in practice. Suppose a factory uses 3 different machines, M1, M2, and M3, to produce the same type of light bulb. We know that machine M1 produces 30% of the total bulbs, machine M2 produces 50%, and machine M3 produces 20%. We also know the defect rates. The probability that a bulb from M1 is defective is 2%, from M2 is 3%, and from M3 is 5%. If we pick one bulb at random from the warehouse, our goal is to find the probability that it is defective. Let's break this down into a step-by-step solution. Step 1. Identify the partition, which represents our causes. As we discussed in the previous slide, these paths must cover all possibilities. Here, the bulb must have been produced by one of the 3 machines. Let's denote the event of a bulb coming from M1 as E1, M2 as E2, and M3 as E3. Therefore, the probability of E1 is 0.30, E2 is 0.50, and E3 is 0.20. Step 2. Identify the event of interest, which is the effect. Let event A be the event that the bulb is defective. We are given the conditional probabilities. The probability of a given E1 is 0.02, the probability of a given E2 is 0.03, and the probability of a given E3 is 0.05. Step 3. Apply the theorem of total probability. We will sum the probabilities of each individual path. The formula is the probability of A equals the probability of E1 times the probability of a given E1, plus the probability of E2 times the probability of a given E2, plus the probability of E3 times the probability of a given E3. Step 4. Substitute the values and calculate. 0.30 multiplied by 0.02 gives us 0.006. 0.50 multiplied by 0.03 gives us 0.015. And 0.20 multiplied by 0.05 gives us 0.010. Adding these 3 results together, we get 0.031. In conclusion, the total probability that a randomly selected bulb is defective is 0.031, which is 3.1%. Now, as we move to the next slide, I want you to pay close attention to how we organized our data, because I will highlight some common pitfalls where students often make mistakes when setting up these exact types of calculations. Common mistakes to avoid. First, a very frequent mistake is confusing the probability of a given E with the probability of E given A in our previous example. We were looking at the probability of a defect, given that it came from a specific machine. That is a given E, however. Many students accidentally flip this and try to find the probability that a bulb came from a specific machine, given that we already know it is defective. That would be E given A. It is important to remember that the theorem of total probability is used to find the overall probability of A, which is actually the first essential step you need to take before you can even attempt to solve for E given A using Bayes' theorem. Second, please be careful not to ignore the requirements of your partition. For this theorem to work, your events, E sub 1, E sub 2, all the way to E sub n, must cover every single possibility without any overlap. A great way to check your work is to sum up the probabilities of all your paths. If the sum of P of E sub j from j equals 1 to n does not equal 1, then your partition is incomplete, and your final answer will be incorrect. Finally, watch out for the temptation of simple addition. It is very easy to look at all those conditional probabilities, the probabilities of the event occurring on each path, and simply add them together. But remember, as we saw in our derivation on slide 3, you cannot just add the conditional probabilities. You must multiply each conditional probability by the probability of the path itself, which is P of E sub j, before you sum them up. Always remember to account for the weight of each path. Now that we have seen how to apply the theorem to our light bulb example, I want to pause and highlight some common pitfalls. Even students who understand the logic can sometimes stumble on these 3 specific areas. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to wrap everything up and consolidate what we have learned today. First, let's revisit the core purpose of this theorem. As we discussed in our opening slides, the theorem of total probability is our go-to tool when we want to calculate the overall probability of an event. Let's call event A. That can occur through several different, distinct, and mutually exclusive paths. It's all about finding the big picture probability by looking at all the different ways an outcome can happen. Second, remember the fundamental requirement. For this theorem to \text work, you must have a partition of the sample space. As we saw in our second slide, this means your different scenarios, which we label as E sub 1, E sub 2, all the way up to E sub n, must cover every single possibility without any overlap. If your paths don't account for the entire sample space, your final calculation won't be accurate. Third, let's look at the underlying logic. If you ever forget the formal notation, just remember the logic we used in our light bulb example. The total probability is simply the sum of the probability of choosing a specific path multiplied by the probability of the event occurring once you are on that path. It is a weighted average of all the different scenarios. Finally, let's look at the formal mathematical formula one last time. The probability of event A equals the summation, from j equals 1 to n, of the probability of E sub j, multiplied by the conditional probability of a given E sub j. I hope this summary helps clarify how all these pieces fit together. Keep practicing with different scenarios, and you'll master this in no time.